Today, we're going to put on our detective hats and dive into a really cool technique called the virus inactivation assay. Think of it as the CSI of the science world, where we're trying to answer one of the most important questions in all of medicine. And here it is, the big question. Let's say you found a new compound, maybe from a plant deep in the rainforest. You've got a hunch it could fight off a nasty virus, but how do you actually prove it? You can't just jump to human trials, right? Well, this procedure is pretty much the very first step to finding out if you're onto something big. Okay, so here's our roadmap for this investigation. We're going to start with the mission, then we'll meet our key players, run the actual test, gather up all the evidence, and finally, deliver the verdict. Let's get into it. First things first, let's set the stage. You know, every great scientific journey starts with a really clear goal. And when it comes to virology, finding new antivirals, that is a massive quest. So, our mission, should we choose to accept it, is pretty straightforward, but also super important. Can we find something, we'll just call it an extract, that can stop a virus dead in its tracks? This whole assay is basically a screening tool. It's that first critical hurdle to see if a compound is even worth a second look. All right, every detective story has its main characters, right? In our little lab experiment, we've got 3 major players, and each one has a very specific role to play in this whole drama. So first, meet the virus. This is our culprit, the bad guy that wants to infect everything. Then we have the extract, our potential hero. We're hoping it can save the day. And finally, we have the viro cells. These are living cells that are going to act as the potential victim in our story. And this right here, this is our master plan. This diagram lays out the entire process, A to Z. I know it might look a little complicated at first glance, but don't worry, we're going to break it down piece by piece. Now, any good investigation starts with knowns. You can't just be random. We start with a very specific amount of our virus, 10 to the 5th power, or 100,000 plaque-forming units. So, what on earth does that actually mean? Let's break it down. A plaque-forming unit, or PFU, is how we measure infectious virus. The absolute best way to picture it is like this. Imagine a perfectly green, healthy lawn of cells. A single PFU is like one drop of poison that kills a little patch of that grass, creating a dead spot. We call that dead spot a plaque. So by counting these plaques, we can count how many active viruses we have. Simple, right? Okay, so we know our mission, we've met our suspects, it's time to get our hands dirty. Let's see how the first part of this experiment actually goes down. It's time to run the test. This first phase is all about giving our hero a fighting chance. We take that specific amount of virus, we mix it with our test extract, and then we just let them hang out together. We incubate them for 2 hours at 37 degrees Celsius. So why do we do this? Why let it just sit there? Well, this incubation step is absolutely critical. The 37 degrees mimics human body temperature, and the 2 hours gives the compounds in our extract enough time to actually find the virus particles and hopefully disable them. We're literally staging a microscopic battle right there in a test tube. Now listen up, because this next step is so important if you want a result you can trust. We do a bunch of high dilutions. Why? Well, it's pretty simple. What if our extract is just plain toxic to the cells? We have to wash it away so that if the cells die later, we know for sure it was the virus that did it, not our hero extract. This makes sure we're testing for antiviral power, not just general toxicity. All right, the battle in the test tube is over. Now it's time to find out who won. We need to introduce whatever's left of that virus to our potential victims, the viro cells, and start gathering some hard evidence. So we take our diluted mix and pour it over a plate of those healthy viro cells. Then we incubate it again, but this time we're waiting to see if any of the surviving viruses can infect the cells and create those dead spots, those plaques we talked about. After a few days, it's time to count them up and see what we've got. If we look back at our master plan here, you can see this is the final stage. We add the mixture to the cells, and we wait. And at the end of it all, we're just counting the dead spots. And you gotta remember, every single plaque we see represents one virus that our extract failed to stop. And here we are, the moment of truth. All that work, the preparation, the waiting, it all comes down to this. By comparing our test sample to a control, we can finally deliver the verdict. Now, what's really important here is the comparison. We always run a control sample that just has the virus, no extract at all. And in that one, as you'd guess, the virus just goes wild and creates tons of plaques. But
In our test sample, if our extract actually worked, we should see way fewer plaques, maybe even none at all.
And that's really the whole story, right there. That visual difference says everything. If the plate with our extract has way fewer dead spots than the control plate, well, we have our proof. The extract successfully neutralized the virus before it ever had a chance to infect the cells. Case closed. Getting a positive result like this is incredibly exciting. I mean, it means our extract is a promising candidate, something we're studying more. But, and this is a big but, we have to remember, this is just step one. Proving something works in a little plastic dish is a long, long way from having a safe and effective medicine for people. It's the start of a very long journey. Which leaves us with this final thought. We've shown our extract can stop a virus in a dish, but what are the massive hurdles that are still in the way of turning this into a real medicine that actually helps people? That's the billion-dollar question every scientist asks after a result like this. Thanks for joining our investigation today.